All right, here we go. This is our lesson on the binomial theorem. It's one of the applications of combinations, of combinatorials. And it starts with kind of a basic problem that I'm sure you've hit before. How do you expand a binomial? Well, everybody knows what a binomial is, right? A binomial is, of course, a polynomial with two terms, right? Like a bicycle has two wheels, a binomial has two terms. So you can kind of just say that every binomial is a plus b. I mean, it could be x plus 3, it could be 7x minus 4y. I mean, you could have anything as long as it's two terms separated by plus or minus, and you'd call it a binomial. Two terms that you can't actually add together and combine because they're not like terms. So that's what we call a binomial. And I'm sure everybody has at some point hit a question like, well, how do you find x plus y cubed? Well, they've given me the answer here, but do you understand how you'd get it? You don't have to write this down, but of course, x plus y squared is x squared plus 2xy plus y squared, right? You learned that in grade 10 when you learned how to FOIL. And if you want to find what x plus y cubed is, keep in mind you'd have to now times that by another x plus y. So like I said, you don't have to write this down. It gave you the answer here, but here's where the answer comes from. Take x times all those terms. Now take y times all those terms. And as you can see, you get a couple of like terms here, right? 2x squared y plus another x squared y is 3x squared y. And then xy squared plus another xy squared is, or plus another 2xy squareds is 3xy squared. And keep in mind, these two things aren't alike terms with each other, right? They don't have the same degree on the same variables. So that's as simple as you can make it. Now imagine you wanted to find x plus y to the 4. You'd have to take this thing and repeat the process and then multiply it out again and then collect all your like terms. And when you do that, you get this rather ugly thing. And again, just like I'm trying to sell you something on late night TV, there must be a better way. This is a heck of a lot of work. And expanding binomials, because you have exponents on them, is actually something that pops up in lots of different applications of math. So it's something we should try to have an easier way to do than, I guess we'd call this the brute force method. And we do. We find patterns. When you expand binomials, you'd call the first term your a term, right? So even if it's x or it's 7x or whatever it is, you just call the first term a and you call the second term b. Now the exponent of a, notice as the a goes up, a here is just x, right? So x is to the power of 4, then it's to the power of 3, then it's to the power of 2, then it's to the power of 1. And remember, you could think of this as x to the power of 0 times y to the 4, because remember, anything to the power of 0 is 1. So the exponent of a, it decreases as you expand the binomial in each term. And then think about the b term now. In this case, the b term here, so my a term, that's supposed to be an arrow. My word, sorry, my drawing's terrible. That's the a term, that's the b term. So notice the b term starts off with y to the 0, then y to the 1, then y to the 2. Y to the 0, y to the 1, y to the 2, y to the 3. Y to the 0, y to the 1, y to the 2, y to the 3, y to the 4. So the b1 is increasing by 1 each time. There are always, now let's count this out. When I have a power of 1 on the binomial, I get 2 terms. When I have a power of 2 on my binomial, I end up with 1, 2, 3 terms. When I have a power of 3 on my binomial, I get 1, 2, 3, 4 terms. I think you can see the pattern. There are always n plus 1 terms of an expansion where n is the exponent. Finally, do you notice, what do you think goes in this blank? See if you can kind of figure out what the blank's trying to say. The blank of the exponents of each individual term of the expansion is equal to the exponent of the binomial. So let's take a look at this power of 4 one. So that's x to the 4. So this is a term, this is a term, this is a term, this is a term, this is a term. What do you notice about this? Now, can I point out to you, remember that x to the 3y, that means y to the 1. And this means x to the 1. What word do you think goes in to that blank? Any ideas? Feel free to pop it into the chat. No? Nobody's seeing it? The word I'm looking for is sum. Notice that 4 plus 0 is 4. 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. The exponents in any term will always add to the same thing, to the total of n. So there's all kinds of patterns here that can help us to find ways to not have to do all this work, which is, again, one of the cool things about algebra. It gives you shortcuts, right? Now, where do these coefficients come from? Now, what do I mean by coefficients? Well, the coefficients here are, of course, 1 and 1. 1, 2, and 1. 1, 3, 3, and 1. 1, 4, 6, 4, and 1. Where do those numbers come from? Well, they are actually combinations. The coefficients in the fourth row, or the fourth expansion, power 4, are 4 choose 0, which is 1, 4 choose 1, which is 4, 4 choose 2, which is 6, 4 choose 3, which is 4, and 4 choose 4, which is 1. So, using my knowledge of what we just did, rather than multiplying it out the longhand way like I did a few minutes ago, let's use the binomial theorem. So let's start with what should it look like? It should look like x to the power of 3 times y to the 0. I'm not going to bother writing y to the 0 because I know that's 1. Plus, x now gets one smaller number than 3, and y gets one bigger number than 0. And again, I don't bother writing that 1, I just know it's there. Plus, and now count down the x to a 1, and count up the y to a 2. Now the x becomes power of 0, right? Power of 0. Actually, you know what? I should have actually made more space here. Okay. Mind if I mulligan this? I'm going to give myself more room. You can just write smaller. Plus, and oh, I don't need the room there. Ugh. X to the 2, y to the 1, plus x to the 1, y to the 2, plus, and then x to the 0, y to the 3. Right? So again, the y exponents counted up, the x exponents counted down, but the sum of the exponents is always 3. Can you see that in the pattern? Because this is 3 plus 0, 2 plus 1, 1 plus 2, 3 plus 0. Now, where do the coefficients come from? This coefficient will be 3 choose 0. This coefficient will be 3 choose 1. This coefficient will be 3 choose 2. This coefficient will be 3 choose 3. And what's 3 choose 0? What's anything choose 0? 1. 3 choose 1 is 3. 3 choose 2 is also 3. And 3 choose 3 is again 1. And that's what it's supposed to be if you look back at what we had before. So there we go. There is how we expand a binomial using combinations. Now, getting these numbers here, that's actually not the only way to get them. Okay? So flip the page. That look familiar? I have a poster of this that I used to have up on my wall. I'll have to put it back one of these days. But ever play with Pascal's triangle? Pascal's triangle is a marvelous, marvelous thing. So Pascal's triangle always has 1s down these diagonal rows. And you get this 2 because you add 1 plus 1. You get this 3 because you add 1 plus 2. You get this 6 because you add 3 plus 3. That's how the pattern works for Pascal's triangle. And there's all kinds of neat patterns in Pascal's triangle. Notice this diagonal here goes 1, 2, 3, 4, 5, 6, 7. Notice this one goes plus 2, plus 3, plus 4, plus 5, plus 6. This is fun. Make a hockey stick. take anything and then make a turn to turn a hockey stick, and 1 plus 2 plus 3 plus 4 plus 5 is 15. There's all kinds of neat patterns you can find in Pascal's triangle. I'll put a link to a YouTube video where a grad student talks about how this is like her favorite thing in all of math, and she actually mentioned some patterns that I didn't know about till I saw the video, and I've seen Pascal's triangle since junior high. But notice I can use Pascal's triangle to say, all right, if n is 1, it's this row. If n is 2, it's this row. If n is 3, it's this row. Actually, wait a minute. Sorry. Hang on. My bad. If n is 0, it's this row. If n is 1, if n is 2. I forgot. You got to start counting at 0. So if n is 3, it's this row. So if I have x plus y to the n, and in this case, suppose I have x plus y to the 3, like we just did, I know that my coefficients are 1, 3, 3, and 1. So that's where I get the 1 x cubed plus 3 x squared y plus 3 x y squared plus 1 y cubed. So these coefficients end up there. Isn't that cool? So let's determine the next line of Pascal's triangle. So we get the next line by just going, okay, well, it's always 1s on the edges. 1 plus 7 is 8. 7 plus 21 is 28. 21 plus 35 is 56. 35 and 35 is 70. 35 and 21 is 56, 21 and 7 is 28, 7 plus 1 is 8. And you could do that forever. Pascal's triangle is an infinite idea. And again, the n plus 1th row is always going to be exactly what you need for coefficients when you expand a binomial. So the connection between Pascal's triangle and the binomial theorem is to look at the nth row to find the coefficients of the expansion. So now, determine the numeric coefficient and the 6th term of the binomial expansion x plus y to the 7. Now when they say 6th term, that means we have to assume that they've organized it in descending powers of term 1 of the x. So, okay, so let's see. If we want x to the power of 7, we have to go to what is essentially the 7th row, and that means I'm counting the first row as the row 0. So 0, 1, 2, 3, 4, 5, 6, 7. So it's this row here. I'm going to highlight it. So it's this row here, right? And my coefficients are 1, 7, 21, 35. So 1, 7, 21, 35, and then another 35, and then a 21. So there's the coefficient on the first term, second term, third term, fourth term, fifth term, sixth term. And of course I didn't really finish it, but after 27 it goes to 1 and then, or 7, then 1 again. So that's the one that I want. So the numeric coefficient of the 6th term is 21. Pascal's triangle tells me that. Okay. Explain a situation where Pascal's triangle doesn't work. Well, if a plus b represents terms with coefficients not equal to 1. Like, for example, what if I was expanding 3x minus 2y to the 7? The coefficient is not going to be 21 on that 6th term now. So how am I going to figure it out? Well, that's where probably using Pascal's triangle it would be way more work than if we go back to using combinations. So back to combinations and back to formulas. It's still a pattern, and the formula looks like this. To find a specific term in a binomial expansion, t to the k plus 1 is equal to n choose k times a to the n minus k times b to the k. There it is. Finally, we've hit the last formula on your formula sheet I handed you at the beginning of the course that we hadn't talked about yet. This is where a represents the first term of the binomial, b is the second term of the binomial, n is the exponent on the binomial, and we use k to find a specific term. For example, if we are asked to find the sixth term of the binomial, we'd say k plus 1 is 6. That would mean k is 5, right? Because move the 1 to the other side, so k is 5. So let's run through an example. This is easier to show you than it is to explain. Find the ninth term in the binomial expansion. So if I want the ninth term, that means that t to the k plus 1 is t to the 9. So that means k plus 1 is 9, so k is 8. So the formula is going to be, oh, and while I'm at it, of course, x is my a, negative 2 is my b, and of course 12 is my n. And I'm using the formula t to the k plus 1 is equal to n choose k times a, that's a k, times a to the n minus k times b to the k. And let me just let me move, give that a little more room here. There. So that's the formula I'm going to use. So the ninth term is 12 choose 8. Why 8? Because k is always 1 more than the term number. What's the a value? A is x. X to the power of n minus k, which is just 12 minus 8, times b, which is, careful, most people look at this and go, oh, b is 2. B is not 2. B is negative 2. And k is 8. Okay, I have a question in the chat that says, is that a 1? Where did I draw something so ugly that you can't tell that it's a 1?
No, it might be. Is that a 1? Just.
Is this a 1? Is that what you're saying?
Yeah, I think he's asking, like, would x be displayed as 1 instead of just x?
X is to the power of 1, if that's what you mean. I'm still kind of not 100% sure what you mean. N choose k. Yeah, n choose k. So that's 12 choose 8. Right? Okay, let me finish this example. He's talking about the k after the c. Oh, yes. Oh, this ugly, ugly k. Yeah, that's supposed to be just a k. Let me write that better. There. Is that better? Okay. All right, let's work this out. So the ninth term is going to be 12 choose 8, which is 495. I punched that in the calculator already. And 12 to the 12 minus 8 is 4, so that's x to the power of 4. And negative 2 to the power of 8 is positive 256. So T9, the ninth term of this expression is, multiply those, you're going to need a calculator for this, obviously. It's 126,720 x to the power of 4. So if you actually took the time, oh, I just realized I wiped out my bracket. If you took the time to actually say, okay, I'm going to start with x minus 2 squared, which is x squared minus 4x plus 4. Now I'm going to times it by another x minus 2, and then you get that answer. Then you're going to times it by another x minus 2, and you're going to get that answer. If you kept doing that until you got to x to the 12, think about how many multiplies that is. The ninth term, so first term, second term, fourth, I mean, you know the first term is x to the power of 12. Isn't that nice? You know that. But after that, it's pretty hard to guess what it is. You'd have to work it out. We just found out that the first, second, third, the ninth term is exactly this. Isn't that a neat shortcut? The binomial expansion is a very cool shortcut. It also doesn't care. One of the great things about math is the rules don't change when the numbers get more complicated. We don't even care if the binomial's kind of ugly looking. Check that thing out. Let's determine the fourth term in the binomial expansion of this mess. Even just squaring this would be kind of a drag, right? Okay, let's see. First times first, outside times outside, inside times inside is the same thing, and last times last. So there we go. There's my expansion for squared. It'd be x squared plus, it'd be, okay, the denominators are the same. So, and then when I add them, it'd be 2. So that'd be x over x squared plus 1 over 4x to the 4. And then, of course, x divided by x squared is just 1 over x. There we go. Look at how much work it took me just to square it. Okay, now times it by another one of these, and that'd be my cubed. Times it by another one of these, that'd be my power of 4. And then another one, and another one, and another one, until I get to x to the power of 9. I'd be here all day. This formula makes this work very, very easy. You just have to know what you're doing. So the formula is, of course, let me write the formula again. T to the k plus 1 is equal to n choose k times a to the n minus k, b to the k. So I just need to know what all those things are. Okay, ninth term, right? Ninth term means that, oh no, sorry, I'm looking for the fourth term. Sorry, fourth term. Fourth term means that k is 3. Always one less, right? Because it's k plus 1 in the formula. N is 9. A is x. First term is just x. Second term is 1 over 2x squared. So let's run that through the formula. The fourth term will be 9 choose 4 times, oh, I just made the calculator pop up and I didn't want to. Go away. Times, okay, what's a again? A is just x, so this is just x to the power of 9 minus 4. Times b, and in this case b is kind of a nasty looking thing, 1 over 2x squared. That's a squared. Now it's a smudge. There we go. And k is, of course, we just figured it out, is oh, hang on a sec. K is, that's a mistake. Somebody hopefully noticed. K is 3, not 4. Sorry about that. Look at that. I wrote down k is 3, then I decided to ignore my own writing. So there we go. The fourth term is 9 choose 3, which I've already punched in my calculator. It's 84. Times x to the power of 6. Now, careful with this thing. When you cube this thing, remember you're cubing all parts of it. So you're cubing 1, which is just 1. You're cubing 2, which is 8. And you're cubing x squared, which is x to the 6. And check that out. Look at how this simplifies. What's x to the 6 divided by x to the 6? Yeah, it's just 1. So this is actually 84 over 8, which is 21 halves. This term doesn't even have an x in it. Isn't that cool? Somebody in the chat just said, how do we find n? N's right there. N is the exponent. Okay. That answer your question? N's the exponent. Right? N, A, B, and K plus 1. Right? So K plus 1 is 4, so K must be 3. And that's it. That's the only 4 pieces of information you need to solve these kinds of questions. So there's already some textbook practice ones. You, of course, have a worksheet in your workbook. But we can actually apply this stuff to kind of other situations. We can use this sort of skill to do some fancier things. Like, for example, suppose I wanted to do something even more specific than just say, oh, let's find the 4th term or the 5th term. What if I said something like, what's the term that has an x to the power of 4 in it when you simplify it? All right, so let's run through how we do this. So again, we already know looking at this that n is 11, a is x squared, and b is negative 2 over x. But what we don't know is k, right? We know that we're looking for term k plus 1. We know that this term will have an x to the power of 4 as its variable. Please notice that if all I care about is the variable, I don't care at all about what the coefficient is. So this part doesn't really matter to me. I just know that the term I'm looking for is x to the power of 4, and then again, a is x squared, b is 1 over x. So this equation allows us to find the value of k. Notice that this is basically exponential work like we did in the last unit. So here's the math on that, right? X to the power of 4, that's a 4, is equal to x to the 2 to the power of n minus k. What do you do in exponents when you take power of a power? Well, you multiply them together. Oops. And while I'm at it, how about I change 1 over x to x to the negative 1? And then again, I've already kind of simplified this one. But this one now I can simplify to that. And what do you do in exponents when you're multiplying two powers that have the same base? You add the exponents. Is this looking familiar? This is just like what we did in chapter 7. So that's 2n minus 2k add negative k. And then I can say that that's, therefore, this base and this base are the same, so these two exponents must be the same. So 4 is equal to 2n minus 2k minus k. Oh yeah, and we know n, don't we? We know that n, don't forget, we knew that up here, n was 1. So I can substitute a 1 for there, and 4 is equal to 2 minus 2, why don't I add those together? Minus 3k. Move the 2 to the other side, and isn't that cool? K is negative 2/3.
Mr. Kellogg,
Yep.
it's 11, not 1.
Oh, what? Oh yeah, thank you. Well, that's a different answer then. Can I change that? Pardon me. So let's see. So that's all right. There. So 2 times n minus again 3k. So that's 4 is equal to 2 times 11 minus 3k. Oh, that's going to be a more reasonable answer. So that's going to be 4 is equal to 22 minus 3k. So move the 3k to the other side, move the 4 to the other side, and then k is 6. Okay, so now k is 6. So what's my answer? And I'm kind of run out of room. They don't give me a whole lot of room on this page. If k is 6, t is k plus 1, so therefore k plus 1 is equal to 6 plus 1, which equals to 7. So therefore, the answer to this problem is the term that has x to the power 4 in this expansion would be the 7th term. There is another way you could do this. If you didn't like all the algebra tricks I just did, you could do this by counting. You could say, all right, I know that my first term is, remember that the exponents always have to add up to 11, right? Because again, n is 11, not 1, thank you very much. N is 11. So you can always just say, well, I know that I take my a value to 11, and my b value, which is, again, we don't have to worry about the coefficients. If there's people going, how come you didn't include the negative 2? We don't need the negative 2, because we don't need coefficients. We're just worried about which one of these is going to end up having x to the 4. We don't care what comes before the x to the 4. So this has an exponent of 0, right? So that would be x to the 22. And then let's see if we can find a pattern. What happens on term 2 to these two things? Well, the x squared, what's the pattern again? This number gets smaller by 1, and this number gets bigger by 1. So that's going to be x to the 20 times 1 over x, which is x to the 19. What's term 3? The a value gets 1 smaller for its power. The b value gets 1 bigger. That's x to the 18 times 1 over x squared, which is x to the 16. So, okay, keep that pattern going. In fact, that's probably enough. Here's my pattern, right? 22, 19, 16. When will I hit 4? That's the first, that's the second, that's the third. What's that one? Does this look familiar? Actually, this is grade 8 or grade 7 algebraic patterns, right? If I have the first thing's 22, the second thing is 19, the third thing is 16, which thing will be 4? Do you remember how to solve a problem like that? Go back to junior high math. You can keep counting if you want to. You could just count, okay, 16. Notice I'm just minusing 3 each time. You can just keep minusing 3 until you hit 4. But of course, there is a more elegant algebraic way to do that. You could just turn this into a xy linear equation, right? Thus, y is equal to negative 3x plus, go back to 0 for your y-intercept, 25, right? Oh, my computer's making weird noises. Okay, so y is equal to, I would like to know when y is 4. Right? And so that would be 4 minus 25, that's negative 21 is equal to negative 3. So x equals 7, so therefore that will be the 7th term. So there you go. 2 completely different ways to approach the same problem. You can count, or you can use the formula. Both of them give you 7. They both kind of have tricks to them, right? But there you go. That's one type of problem we can do with this stuff. Example 2. Determine the constant in the binomial expansion. Now, we've kind of already seen this by kind of coincidence. When we were solving this one here, we were looking for the 4th term, but look what happened in the 4th term. In the 4th term, the x in the numerator and the x squared in the denominator ended up canceling each other out, and we ended up with a constant. So that's what we're looking for here. We are looking to see which term will make the constant. That means that the variable has an exponent of 0. So that means, and I'll do this kind of the first way again, right? That means that t sub k plus 1 is equal to n choose k times a to the n minus k times b to the k. So I want the term p to the 0. And I don't care about this part, because again, I don't care about the coefficient. I only care about which term is the constant. So, which term is this? A here is 3p. N is 18. K is what I'm looking for. I don't know which term it is. B is negative 1 over p. And again, k is what I'm looking for. Now again, I don't care about coefficients, so that means this 3 and this negative 1 don't matter to me. So that's p to the 18 minus k times p to the, change that to an exponent, negative 1 to the k. And there we go. I can now make that p to the 0 equals p to the, add those exponents together, 18 minus k minus 1. Or sorry, minus k, not minus 1, minus k, right? Minus k, because negative 1 times k is negative 1k. And then I can turn that into an equation. Therefore, 0 is equal to 18 minus 2k. So 2k is equal to 18, so k is equal to 9. So now that I know k is 9, I can go back to this formula and put in everything I'm looking for. So k is 9, so it's actually, if k is 9, then this is the 10th term. And the 10th term, so t sub 10, is going to equal n, what was n again here? I've already forgotten what n is, 18. 18, choose, k was 9, right? Times a to the 18 minus 9 times b to the 9. See, now that I'm actually finding what the term is, I'm putting back all the coefficients. So now that I figured out k, I can figure out what the entire term is. So 18 choose 9, I had to punch on a calculator, and I got 48,620. 3p to the 9, I'll just do this in steps so that I don't get lost, and negative 1 over p to the 9. Right? A negative power, or sorry, a negative base will still be negative when you take it to an odd power, so that negative's still going to be there. Why don't I make my life easier and just move that negative to the front of the entire number? And then I'm going to again use my calculator and take 48,620 times 3 to the power of 9. Which, here, I'll show you the calculation. It's 48,620 times 3 to the power of 9 is another 19,683. And of course, p to the 9 divided by p to the 9 is going to cancel. And that was the whole point, right? We wanted to find the constant term. So it turns out the constant term is the 10th term, and it's negative, whatever that answer is. It barely fits on my calculator. It is, let me write it out. Let me write it out backwards so I get the spaces right. 460 space 987 space 956. 956,780,000, sorry, I said that wrong. 956,987,460 is the constant. If I expand this thing, which had a big power of 18, the 10th term will be the constant. Imagine how much work it would have taken to figure that out if you didn't have this formula, if you didn't have this shortcut, which is super, super cool. Right? And I actually this kind of had its own check built into it, because the fact that those things canceled means that I know I did it right, because my whole goal from the very beginning was to find the term that didn't have a variable in it. So this stuff is fun. Okay, let's do one more example. And then I think there is only one more example in this lesson, right? Yep. Okay, so this is it. Last example. So determine the value of n if the 5th term is 280x squared. Okay, once again, I'm not going to worry about this 280 right now until I find k. K is just involves the exponents on the variables. So let's focus on the variables, right? X squared is going to equal the first thing, which is an x squared, times some n minus k. But oh, I know k this time. If it's the 5th term, then k is 4. So that's n minus 4 times, and again, I don't care about that -1, I just care that it's 1 over x to the k, and that will give me n, right? So let's see what we can do with that. So that's going to be x squared equals x to the 2 times n minus 4, so 2n minus 8. And I can switch this to an x to the -1 if you like. Simplify it one more time. It's a negative now. And then remember that if I can turn this into one single base on each side, add those exponents. 2n minus 8 add -4 is 2n minus 12. Now I can say, therefore, since the base is the same on each side, the exponents have to be the same. 2 is equal to 2n minus 12. Add 12 to both sides. Divide both sides of the equation by 2. And once again, that's the exponent. So I know that this is the 5th term if n is 7. And notice I didn't have to worry about the coefficients at on this one at all. If it actually did say find what, expand this to some other number, then I'd have to use the formula and put in the choose and all that stuff. But there we go. That's the binomial theorem. These, of course, take practice. Tomorrow we don't have a class, so I really wanted to get through. Usually I split this lesson in half and kind of cut it off after where's that textbook assignment kind of start. I can't remember where the break is, where the textbook assignment was. Yeah, right there. Usually I kind of break it there and then let people do part of the 11.3 worksheet and then do the next lesson the next day. But since we lose tomorrow's class, I thought I better kind of try to get through it all. So that's the assignment. You can now do the 11.3 worksheet in your workbook. And if you want extra practice, there is, of course, always the textbook questions for extra practice. Okay, I'm going to stop my video right now and see if anybody has any questions.